what? I'm going to do it the other way. I'm going to take a negative out of this one. That doesn't matter. So put a negative here. Which one do you want it out of? Take a negative out. 2 minus x squared. Okay. Something looks wrong. Oh, that's the base of half the triangle. That's the problem. Okay. Yeah, I was like, this is not right. That's going to give us a negative number. Okay. Hold on. We're back here, right? Okay. We need to be looking at this. Yeah, we doubled it, though. We doubled it already. We doubled it. So this right here was root 3 times x squared minus 2, like that. And it was x squared minus 2, right? Yeah.
X squared minus 2 squared.
But we took the square root because this was h squared. H was the root of that, right? So I took the root of this, and that's where I got this. Okay, man, you know what? I don't even care because my way is so much easier than this. That can we just pause? Can we just pause this right now? Okay, let's just pause it. No, I don't want to delete it because you should know how to do this, all right? You should, but okay, there's something very special about an equilateral triangle. Very special. But let me take you back to pre-cal real quick. Well, don't worry about it. It's not going to be that bad. If we have a triangle, all right, like this, it doesn't have to be a right triangle. If this is the base and this is the height, then most people are aware of the fact that the area is 1/2 base times height. That's pretty much known by everybody, right? But there's another formula. Does anyone know the other formula for an area of a triangle that does not involve the height of the triangle? Anyone know? Okay, good. Well, you don't remember then. If you have one angle in the triangle, if I know this angle, the area of the triangle is then 1/2 AB, sine theta. I forgot to label one more thing there. You have to know one side. So if you have a right triangle, if you know the base and the height, you're in business, okay? But if you have two sides in the angle between them, you can use this formula. Have y'all ever seen that formula before? Maybe? Okay, can I show you where it comes from? It's not that bad. I want us real quick to just take a look at this. You see that h right there? That h is not here, right? What took its place? A sine theta. Somehow those are the same, aren't they? According to this being this, that's saying h is equal to a sine theta, isn't it? Okay, so just divide both sides by a. Now look at your triangle. Is that true?
Yeah.
Is sine of theta h over a? So what we do here is, to get to this formula, we draw this picture, then we write down sine of theta is h over a, and then we solve for h by multiplying by a, and then we take that and replace h with it. And we get this formula. Now let me show you what's so awesome about this formula. Is that if we go back to the triangle we were working on right here, right? And we drew that, and then we try to cut it in half, right? We don't need to, because we know this is 60 degrees, because it's an equilateral triangle. Pi over 3 if you like. We know that this side right here is 4 minus 2x squared, right? Yeah. We know that this side is 4 minus 2x squared because it's an equilateral triangle. I have two sides in the angle between them. So the area of this triangle is 1/2 of the base times the height, right? Times sine, so I'm using this formula, sine of 60 degrees. And sine of 60 degrees is? That's the y-coordinate on the unit circle when you're at 60 degrees. 60 degrees, y-coordinate. Root 3 over 2. Root 3 over 2. So this right here is root 3 over 2, right? Multiply that times that, we get root 3 over 4. We get that. There's my formula. That's the formula for the area. See, I didn't need any Pythagorean, nothing, right? right?
Yeah.
Now, I am feeling okay when we were back over here. You see how we had that root 3 in there? I'm glad to see that because I knew it was going to have a root 3 because I knew it was going to be sine of 60 degrees at some point. The rest of it, I don't know. We can work that out later. Let's not worry about that. So what is the volume of this one slab? Of this one little sliver piece? That's the area, right? So it's the area times the depth of it. So it's just root 3 over 4 minus 2x squared dx. Would you all agree that this formula was a lot easier to work with? Okay. Way quicker. Way, way quicker. In my Cal 1 class, when we get to the problems where there's a problem in there where we do something like this, I always point this out. Like this is very useful. All right, now what? We need to add up all those little slivers. So integral, right? Now where are we going to go for on our integral? Negative root 2 to root 2, right? Same thing as before. So the answer to part B, okay? The answer to part B is volume equals integral negative root 2 to root 2 of the formula we came up with, which was root 3 over 4. We could pull that out as a constant, but we're not going to integrate it anyway, right? So who cares? There we go. Sit. That all right?
Can I ask you?
Yes, you may.
Do you need to find like the height?
You don't need the height because this formula doesn't require the height.
Oh no, like when you explain it, when we need to find the volume, you need the area and the height.
Okay, height meaning this height. Well, if I drew my triangle like this, then it's how tall that little cheese slice is. Does that make a little more sense? Okay. Yeah, when we're looking at these like height, length, width, it's all relative. It depends on what you want to call. Like normally, normally height is this, right? And then like width is this. And then, right?
Yeah.
Depth. But if you were looking at it from a different perspective, it would be different, right? So, all right. I said that I put these in order of difficulty, but I just remembered semicircle is going to be even the easiest one, or easier than B. Pardon?
You put them in like opposite.
Yeah, I kind of messed up. Well, you tell me. What does the slice look like in C? So for part C, what does it look like? It's like that, right? It's got a little bit of depth to it, I guess, right? Height, depth, width, length, whatever you want to call it, Sophia. That's dx. How can I find the volume of this? Well, I need the area of that front surface, don't I? If I can find the area of this front surface, I'll multiply it times the height, Sophia. The height is dx, depth, width, length, whatever you want to call it, yes? So I need the area of that little half circle, right? So what is the area of this half circle? What is its area? Do I know anything? Do I know any pieces of it? I know the diameter is 4 minus 2x squared. That we've already established, right? So the area of a circle is pi r squared, right? So half of a circle should be half of pi r squared. But this is the diameter, so what's the distance from here to here? What's our radius? It's not that, it's half of that, which happens to be 2 minus x squared, right? So that's actually my radius. I'm sorry?
This one's actually easier.
Yeah, that's what I was saying, that I should have put the equilateral triangles last. So what is the area of this? The area is going to be half of pi r squared, right? Because it's half of a circle. And so that is 1/2 of pi times my radius, which we just established was 2 minus x squared, right? Squared. So half of pi times the radius squared. And then the depth of it or height of it or thickness of it, whatever, is dx. So I put all those, multiply them together, that gives me my volume. And so I think I can go straight to the integral if you're okay with that. Volume is negative root 2 to 2, root 2. I could pull out the 1/2 pi, but I didn't pull out the root 3 over 4, so I'm just going to leave it there. 2 minus x squared squared dx. And you understand like how we could get these, right? Like, you know, just expand it, and these are just power rules. Like none of these integrals would require any techniques of integration. Like all of these would just be pretty straightforward, wouldn't they?
You take out that, if we were to solve it, you take out the square root of 3 over 4 halves?
Mhm.
Yeah, right.
Okay. All right.
Yeah, those triangles.
That's it for that. Yeah, those triangles are a little messy, but not with that other formula. It's such a great formula. All right, we are now officially done with 8.2. And 7.2 and, sorry, 7.2 and 7.3. Yeah, no. Yeah. All right, so now we're going to talk about arc length. I have about 20 minutes. 7.4. Oh, you know what? Perfect, perfect, perfect. Somebody left their lightning cable charger over here. My daughter will appreciate that. No, I'm just kidding. I need the cable. All right, so look. We have a function. Say it starts here, goes there, right? We've already discussed in this class how we could imagine dropping down dotted lines and finding the area under that, right? We could wrap that around the x-axis using washers. We could wrap it around the y-axis using shells, right? In Cal 1, we could take the derivative of that and find slopes of tangent lines, right? So we're going to do something very different now, and we're going to look at, if we took this curve, right? There's the curve. It's almost like this wire was made to do this. Look at that. It's got the proper bends in it. Okay, so look, we've got that. Now imagine we take that off the page, right? And we take it over here, and we straighten it out and mark it, right? Mark it here to here to here, right there. How long is that? That's what arc length is, all right? It's a measurement of the arc, the length of the arc, right? Pretty straightforward. Now, how do we get it? Well, believe it or not, we're going to use an integral again. So imagine that I pick some point here, x, right? And I go up to the curve and I'm on the curve. And let's mark these as A and B, all right? A and B, like we did before. These are our starting and ending points. So imagine that I go in there and I zoom in, okay? I zoom in. And I'm going to pick actually not just this point, I'm going to pick a point right next to it, really, really close, like infinitesimally close to it. And then I zoom in. I zoom in and I've got this point there, well, I'll make it real big, and then that other point I picked next to it was over here. And then I've got the curve going through the two, right? I'm zoomed in, so I've got this curve, it's a massive curve because I'm zoomed in. No. And then it goes through, comes out, right? Yes? I want to know how long this curve is right here. I want to know how long this is. Right? That little piece, I'm zoomed in on this. Well, one thing I could do is I could imagine drawing a little right triangle here. And if I draw a right triangle, there's going to be a straight line between those points, aren't there? Yeah. Now that straight line, the length of that straight line is pretty darn close to the length of the red one. But there's some error. Isn't there some error in there? The error is there because this is a curve, not a straight line. But remember, just like we did with the rectangles. Remember with the rectangles, we said, look, we have a rectangle, but we're going to make them get more narrow, right? And basically infinitesimally thin. That's essentially what I'm doing here. I'm picking 2 points that are going to become like infinitesimally close to one another, which means the error that we have there is starting to diminish and go to 0. Okay? That's what the limit's going to allow us to do, right? So how could we figure out what's the length of the blue line? Well, it's the hypotenuse of a right triangle, yes? Yeah. So if I knew how long this was and how long this was, I would have some idea. Now, would you agree that as I move from here to here, I have to first have some sort of change in x, right? And then when I move from here to here, I have some change in y, delta y. But if we take the limit and we let these points get right close to one another, then delta x and delta y get replaced with what? What have we done when we've taken a limit? Delta has changed to what? dx and dy, all right? So in the limit, as this thing starts to come together, this becomes dx and this becomes dy. Does that make sense to you? Kind of, visually, intuitively? Does this make sense?
Because we're going to take the integral?
Nope, integral's not here yet. Nope, just the idea that if you go from one point to another on a straight line, you have to have a change in x and then a change in y. Okay? You might have to actually go back and look at Cal 1 to understand this. When we were trying to find the slope of the tangent line here, what we did was we started with a secant line. So what we did was we grabbed a point over here and we started to march this point closer and closer to this point and watch what that secant line did. And when we got it right there, we could never put the point right on top, because if we did, we get 0 over 0. But in the limit, we could find in the limit what it approached. And that's what when we do the limit, it becomes, well, in the limit, it becomes, what's rise over run here? What's rise over run? dy over dx. And dy over dx is the derivative, right? And that represents the slope of that line, rise over run. Yeah? Okay, you buy that?
Yeah.
Okay, okay. All right, so we've got this little triangle, right? Now let's use, if we're trying to figure out what this blue line is, I'm going to call it little l for the length of that blue line. Then little l squared equals this squared plus this squared, right? So dx squared plus dy squared. That's Pythagorean, right? A squared plus b squared equals c squared. So that means L is the square root of this. I'm going to write it a little different. Dx squared plus dy squared. Are y'all all right with that? So if I pick some point x in here, and I go in there and I take this little infinitesimal little cut and try and measure the length of it, it would be the same as measuring the length of the blue. And then in the limit, we let these kind of get really infinitesimally close. And this would be the measurement of that little infinitesimal little piece. This is it right here. So I would have a measurement of this little tiny piece. But then I'd want to move x over a little bit and then do it again, right? So I want to add all these up again. I want to add this length up with the next little length, with the next little length, with the next little length, right? So I want to do this integral. I want to do, so the total length of this, capital L, should be the integral from a to b, because I'm letting a go to b, right? Yeah. So, I'm sorry, I'm letting the x start at a and end at b. But I'm trying to add up all these little l's. Yes? That's what I'm adding up. Just like we had to come up with a formula for our little slabs, now we're trying to come up with our formula for our little lengths. And we add them up, so we want to integrate this L. That formula in there is problematic. What's problematic about it is the fact that we've got some expressions in here that don't make a lot of sense to us. Like, what is dx squared? What is dy squared? What is it? What does that mean? And then in all of our integrals, haven't we always had a little dx in the back? Right? Okay, so watch me. I'm going to force the dx to come out the back side. Tell me what I'm doing. Tell me what I'm doing here. What did I do there? I factored a dx squared out of here and here. When I pull a dx squared out of here, it becomes a 1. When I pull a dx squared out of here, well, there is no dx squared, right? So I have to divide by dx squared. So it becomes dy over dx squared. Agree? Now, dx, the square root of dx squared times this, I can actually take the square root of dx squared, and that'll come on the outside as a dx, right? And I can slap that to the back. And then what's left inside? 1 plus. And do you remember what this is? I mean, what's dy dx from Cal 1? That's the derivative of the original function, right? That's the derivative of the function squared. Then we have dx on the outside. Now, it came out to the front, but then I slapped it to the back. And that's our formula. If you give me a function f, okay, you give me some curve f, and you want to know how long it is from here to here, right? If you want to know how long that is, then I need to be able to compute the integral of the square root of 1 plus the derivative of the function squared. If I can do that, I'm in business.
So you're going to have a function in there, and you're going to find the derivative, and then find the antiderivative?
Yep.
I don't expect
It's weird, right? To find the length of some function f, I'm going to have to find the antiderivative of some algebraic expression that involves its own derivative. Right? That's weird. It's weird. But I mean, if you think about it, it's kind of like we're trying to move from left to right, and we're trying to add up all these little infinitesimal lengths, right? And each one of these infinitesimal lengths, we're somehow using the derivative to give us like a slope, but that slope is actually in some way representing like the length of each little step as we move along. It's weird, but it is what it is. Yes? Yeah. All right, now let's see it in action. I'm going to try one. I don't think we're going to be able to get it, but let's try it. Show C equals 2 pi r. So I've made my best effort in this class to show, in class I have shown, or we have shown together, that the area of a circle of radius r is pi r squared. We have also shown that the volume of a solid ball of radius r is 4/3 pi r cubed, right? Now, it's almost like we're taking steps backwards here. I want to show that the circumference of a circle is 2 pi r. Okay? So what do I need to do that? Well, how about we find how long that piece is, and then multiply it times 4. Yes? Could we do that? Okay, well, if I'm going to take that little piece and find its length, I need to be able to write that red thing as a function. And we've done this now. This is the third time we've done this. So hopefully we all remember what that curve is. Y equals square root r squared minus x squared. This was r, right? The equation of the circle is x squared plus y squared equals r squared. You solve for y. You get that? Agree? Okay. Now, according to the formula I just gave you, the length of that red piece right there will be the integral from where to where? From 0 to r of the square root of 1 plus the derivative of that, right? Squared. So aren't we going to need to go do that over here on the side? Okay, let's do that on the side. Our f of x in this problem is square root of r squared minus x squared. What is the derivative of this? Well, yeah.
Can't you write that a different?
You can, and I would trust that you could do this if you had enough time, right? That would be the derivative of that. And you'd get some cancellation here of 2's. So your derivative is negative x over square root of r squared minus x squared. That's our derivative, right?
Do you think we ripped up the inside?
I did. That was this?
Yeah, the R disappears.
Yeah, the r is a constant, right? So derivative of a constant is going to go away to 0. Is that okay? Now that's the derivative, but what goes into the formula? The derivative squared. So let's go ahead and do that over here now too. The derivative squared is, just square the top and bottom of this. Well, that's x squared over r squared minus x squared. So that's kind of nice. The negative goes away because we square it, and then on the bottom the root goes away, right? And that gets to get plugged in right there. So that goes right here, x squared over r squared plus x squared dx, right? So the big formula, length equals integral a to b of square root of 1 plus f prime of x squared dx. That's our formula for arc length, okay? That's going to go the rest of the way with us in this class. All right? Yay, we get to integrate that. That does not look pretty, right? I wouldn't care so much if I didn't have the root on the outside of everything, right? That root on the outside looks pretty bad. Do you agree? But let's start off on the inside. Let's just start with a common denominator on the inside. So let's just put like this, get these two together. So I'll have to do r squared plus x squared here, r squared plus x squared there. Is it minus? Oh, yeah, minus. Thank you, thank you, thank you. I'm not sure what we're going to do yet. Yeah, I haven't worked this problem out. So 0 to r. I said in the beginning we may not be able to do it, okay? But it seems like the answer's so nice, right, that we should be able to get this. Okay, so let's see. We go r squared minus x squared goes on top. And then we still have an x squared up there, right, from this one. And that's all over our common denominator of r squared minus x squared, and then dx. And we got good news upstairs, right? X's cancel. I think I'm going to come back. I'm going to come over here. And this is going to be integral 0 to r. Okay, what was left on top? R squared, but you're taking the square root of it, right? Which is just r. R on top, and then square root of r squared minus x squared dx. What about that r on top? It's a constant. It can come out, can't it? That can come out. So this is going to be r. Hey, look, I have an r in my answer too, so I'm pretty happy about that. Okay, r here, 0 to r. And then I have 1 over the square root of r squared minus x squared dx. And that, yes, would be trig sub. However, we actually have a formula for this one. Look it up. Arc sine. Go look on your formula sheet. Just verify you can find that. We do have that formula. I wanted someone to give me the number on it, but formula 16. Formula 16. Formula 16 says that if you have, 1 over the square root of a squared minus u squared, where u is your variable, the answer is arc sine of u over a. Sorry about that. I forgot to mute that. What does it say it is? Arc sine of u over a. So the variable over the constant here. So this should be r times arc sine of, what's our variable? X over, what's the a for us? R. And then we still need to do a definite integral here. So what's our definite integral? 0 to r, right? Okay, this is going to be actually really nice. Let r go here, right? You get r over r, which is 1. Arc sine of 1 is saying, where's your y-coordinate on the unit circle 1? At what angle? Pi over 2. Pi over 2, right? So we have r, that's this, times pi over 2. That's what we get when we plug in r. And then minus, now arc sine of 0. So what's arc sine of 0? At what angle is your y-coordinate 0? At 0. So you get 0 here. So our answer is half of pi r, right? Half of pi r. And that's only that was only 1/4 of it, remember? So when we went, we only found that piece, right? So if we multiply that times 4, we get 2 pi r.
Also, we use tricks, we would have to use the.
If you would have used trig sub, yeah, you would have used sine x is equal to r sine theta. It would have worked out. Yep, it would have worked out, but see, the formula was a little faster. Yeah. Okay, how much time do I have? 9 minutes? And I'm supposed to talk about the exam? All right, so I'll be honest with you. I'm kind of